Section 6.3, Sampling Distributions and Estimators. We're now going to consider the concept of a sampling distribution of a statistic. So instead of working with values from the original population, we're going to focus on values of statistics, things like sample proportions and sample means that we obtain from the population. When samples of the same size are taken from the same population, the following two properties apply. Sample proportions tend to be normally distributed, and the mean of sample proportions is the same as the population mean. And here's a little pictorial of what's happening when we do that. When we take multiple samples and then we form a histogram of the means of those samples, we'll see that it looks like a normal distribution. And that happens with sample means and also with proportions. So the sampling distribution of a statistic, such as the sample proportion or sample mean, is the distribution of all the values of the statistic when all samples, possible samples of the same size n are taken. The sampling distribution of the sample proportion is where we talk about just simply the proportions, and here we're working with the sampling with the variable, the statistic p hat. And again, let's remember that p, simply just a letter p, is the population proportion, and then p with a hat on it is the sample proportion. And that means we have the parameter and the statistic. So the behavior of sample proportions, the distribution of sample proportions tends to approximate a normal distribution. The sample proportions will target the value of the population proportion in the sense that the mean of all the sample proportions will be equal to the population proportion. Consider the following process. We're going to roll a die 5 times and find the proportion of odd numbers. That would be a 1 or a 3 or a 5. What do we know about the behavior of all the sample proportions that are generated as this process continues indefinitely? And if you notice here, what will happen is we end up again, and this is where we did it ultimately 10,000 sample trials, we have a nice normal distribution, which is what we expected based on what we just said. Now, the sampling distribution of the sample mean follows a similar process. The sample is the distribution of all possible sample means, and that referring to the variable x bar, with samples having the same sample size taken from the same population. And the behavior of the sample means will be the sample mean distribution will tend to be a normal distribution, and it will target the value of the population mean. Consider repeating this process. Roll a die 5 times to randomly select 5 values from the population 1, 2, 3, 4, 5, 6 to find the mean x bar of the results. What do we know about the behavior of all sample means that are generated by this process? Well, we know that the sample mean there, if you remember NP that we learned about with this binomial trial, it would give us a sample mean of 3.5. And here again, here's our histogram. So an estimator is a statistic used to infer or estimate the value of a population parameter. And we say an estimator is unbiased when it targets the true value of the population parameter. And unbiased estimators, 2 of the ones that we're going to use in this class are for the proportion. P hat is an unbiased estimator of the population proportion, and the sample mean x bar is an unbiased estimator of the population mean mu. A biased estimator for example, would be something like the median, so it doesn't actually target the corresponding population parameter. So why do we sample with replacement? Because 2 important reasons. When selecting a relatively small sample from a large population, it really makes no difference whether we sample with or without replacement. And sampling with replacement results in independent events that are unaffected by previous outcomes. Now let's move on to the most important theorem in statistics, the central limit theorem. The central limit theorem says for all samples of the same size n, where n is greater than 30, the sampling distribution of x bar, the mean, can be approximated with a normal distribution with mean mu and standard deviation sigma divided by the square root of n. And that's 2 requirements. The population has a mean of mu and a standard deviation of sigma, and we take simple random samples all of the same size n from the same population. The requirements, the population has a normal distribution or n is greater than 30. Then the mean of all values of x bar will be the population mean, and the standard deviations of all values of x bar will be sigma divided by the square root of n. And we could do a z-score conversion as we notice down here. And notice this is a little bit different than the z-score we used previously because we're doing an adjustment here because we're taking a sample rather than an individual observation. If the original population is not normally distributed or we have a sample size less than 30, then the distribution of x bar cannot be approximated well by a normal distribution, and the methods in this section will not apply. So when you're doing practical problem solving, you want to check your requirements. You want to verify that the normal distribution can be used by confirming the original population had a normal distribution that would be stated, or that you have a sufficient sample size that is greater than 30. And then you want to determine whether you're working with an individual value or a mean from a sample, because it's going to determine which z-score you'll be working with. Remember, for an individual z-score, you're going to use divide by sigma, and when you're working with a sample, you're going to adjust with a standard deviation of sigma divided by the square root of n. If all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, then the mean of all the sample means, as we just stated, is designated as mu, and the standard deviation of all values for x bar is designated by sigma divided by the square root of n, and we frequently call this expression here the standard error of the mean, or SEM. Let's take an example. The elevator in a car rental building at San Francisco International Airport has a placard stating the maximum capacity is 4,000 pounds, 27 passengers. This converts to a mean weight of 148 pounds when the elevator is full, and that comes from dividing 4,000 by 27. We assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume the adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. First, we want to find the probability one randomly selected adult male has a weight greater than 148. And then secondly, we want to find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. So for the first problem, remember we're doing individual male here, so we're going to take his weight of 148 minus the target weight of 189, and then divide by 39 rather, and we get a z-score of negative 1.05. And here's where we fall in the distribution. So we're below the mean here, and then if we go ahead and use technology, or we use a table, and here's the technology. So if we use StatCrunch, stat, calculator normal, enter the mean 189. This is the mean for all the men. The standard deviation of 39, and we want to know how likely it is that the male weight would exceed 148 pounds, and we come up with a pretty high probability. Now, for part B, this is where we have a sample of 27 men. So we can use the normal distribution if the original population is normally distributed or sample size greater than 30. Our sample size was 27, but the problem stated that the males have a normal distribution. The weights of the males are normally distributed, so therefore we can use the methods in this section. And we're going to form a z-score using 189 for the mean and the standard error of the mean as 7.5951, which is 39 divided by the square root of 27, the sample size. And there we go. There's what the distribution looks like now because our standard deviation is much smaller. And now our z-score is negative 5.46. And I'm sorry that this came up a little odd there, but we're going to go ahead and we're going to use StatCrunch anyway. So let's go on to the StatCrunch part. So we enter the mean and the standard deviation now instead of 39 is 7.51, and we still want to find the probability that the mean weight is greater than 148. And now we see that the probability is 0.9999. So we're quite sure that 27 randomly selected males will have a mean weight greater than 148. So the interpretation here is 85% chance that an individual male would weigh more than 148, and an almost certain probability that 27 randomly selected males will have a mean weight greater than 148. Given the safe capacity of the elevator is 4,000 pounds, it is almost certain that it will be overweight if it's filled with 27 randomly selected adults. So what can be done? You could limit the weight capacity or the number of people, or both. Identifying significant results with probabilities, and remember our rare event rule, and remember we did this previously where we simply looked at the mean minus 2 standard deviations and the mean plus 2 standard deviations. So let's assume the population of a human body temperatures has a mean of 98.6 degrees Fahrenheit, and assume the standard deviation is 0.62. If a sample of 106 is randomly selected, find the probability of getting a mean of 98.2 or lower. So we're going to work under the assumption that the population of human body temperatures has a mean of 98.6. We weren't told if it was normally distributed, but our sample size is 106, and that's greater than 30, so we can use the central limit theorem, and we can conclude that we're going to use these parameters. Mu is going to be 98.6, and the standard error of the mean is going to be 0.62 divided by the square root of our sample size, and we get this standard error right here. And then we're looking at 98.2 as our sample mean, and that's well below the population mean. And actually, if you do the z-score, it's negative 6.64. And again, we could use technology. We can also use StatCrunch, which I did right here, and you come up with basically a probability of 0. So it's interesting that z-score there is negative 6.64. It's very, very unusual. So what does this tell us? The results say that if the mean of our body temperatures is really 98.6, as we assume, then there's an extremely small probability of getting a sample mean of 98.2 or lower when 106 subjects are selected. The researchers did obtain such a mean, and after confirming the sample was sound, there's two possibilities. The sample mean really is 98.6, and their sample represents a chance event that is very rare, or perhaps that assumption of the population mean being 98.6 is incorrect and the population mean is actually lower. And let's do a try it. You try it. This is similar to a problem you'll see in the homework. A boat capsized and sank in a lake. Based on an assumption of a mean weight of 143 pounds, the boat was rated to carry 50 passengers. After the boat sank, the assumed mean weight for similar boats was changed from 143 to 170. Assume a similar boat is loaded with 50 people, and assume the weights of the people are normally distributed with a mean weight of 176.8 and a standard deviation of 35.3. Find the probability the boat is overloaded because the 50 passengers have a mean weight greater than 143. So we're going to assume that the population mean is 176.8, and since we're doing a sample here, we're going to take 35.3 and divide by the square root of 50, and we get the standard error of the mean to be about 4.99. We're going to use StatCrunch, and we want to know what's the probability that the mean weight is greater than 150. And we notice here again, the probability is very large, is basically 1. So we're pretty sure that this boat's going to be overloaded. And the z-score for this particular value of 150 is negative 5.47. Very, very unusual. Now, the boat was later rated to carry only 13 passengers, and the load limit was changed to 2210. Find the probability the boat is overloaded because the mean weight is now 170. Okay, so we're going to assume again the same mean weight of 176.8. And we're going to do a standard error of the mean of 9.79. We've decreased the sample. And we're going to use StatCrunch again, and now we come up with a probability of 0.7563, which is still pretty high. So again, what can be done here? Less passengers or lower the weight capacity. So there's still a pretty high probability that the boat would be overloaded. Now the last section in Chapter 6 covers assessing normality, and we mentioned before that we want to know if there's an underlying normal distribution, and there's two ways to look for that. We could do a histogram, or we could do what's called a normal quantile plot. And a normal quantile plot, or normal probability plot, is a graph of the points where x is the value from the original set of data and y is the corresponding z-score that would be expected from a standard normal distribution. So what can you do to determine whether the data comes from a population that's normally distributed? Construct the histogram. If it dramatically departs from a bell shape, conclude that the data do not have a normal distribution. Identify outliers. If there is more than one outlier, conclude the data might not have a normal distribution. Normal quantile plot. If the histogram is basically symmetric and the number of outliers is 0 or 1, use technology to generate the normal quantile plot. And when you look at the normal quantile plot, you want to look to see if the points on that plot follow a reasonably close to a straight line pattern. If they don't, then we don't have a normal distribution. The points do not lie reasonably close to a straight line, or they show some systematic pattern that is not a straight line. I'm going to give you some examples. So here's a nice example of a normal distribution. Here's IQ scores, here's the histogram, nice bell-shaped curve. Here's the normal quantile plot. We might say there might be some outliers here, and you can see perhaps over here, but that looks pretty good. Now here's an example of one with a systematic pattern that is not a straight line. If you notice, it goes above and then it goes below. There's not a random pattern around that straight line. And then here's another one that's a skewed example. This is not a normal distribution, as we can tell from, again, from the histogram. It's not. It's a skewed distribution. So if the requirement of a normal distribution is not too strict, simply look at the histogram and find the number of outliers. If the histogram is roughly bell-shaped and outliers are 0 or 1, we can say it has a normal distribution. Normal quantile plots can be difficult to construct on your own, but StatCrunch does a really nice job for those. So I'm going to do a normal quantile plot for the 250 duration times listed in the Old Faithful data set from your textbook. So if you access StatCrunch from the left toolbar in My Stat Lab, click on Data Sets from the textbook and locate Old Faithful. And then I'm going to select Stat Graph QQ Plot, select the column Duration, and select the other option, Normal Quantiles on the Y-axis. Make sure you click that option right there, and then Compute. And so here's what this looks like. And if I go back and I do a histogram, I notice there's actually two groupings in that. And there's the box plot. And so this is not a normal distribution. It actually looks like it's being pulled from two different populations. So we can see that the histogram is skewed to the left and far from being bell-shaped. There's many outliers. Normal quantile plot, the lines in the normal quantile plot are far from a straight line. We conclude the 250 eruption times do not appear to come from a population with a normal distribution. And here's an example. Sample data for arrival delay times from airport flights are given below. Determine whether they appear to be from a distribution, population with a normal distribution. So we're going to open the data in StatCrunch, create the histogram. And first I did the histogram here, and then that's graph histogram. And then the quantile plot is here. And we notice that this is definitely not normally distributed. We see some outliers over here, which we can see here. So we see outliers, and this also shows a systematic pattern that's not a straight line. It's below the line, and then it goes above it, and then it goes back down below it. So this is not a normal distribution.